Hello, my name is Professor Greg Pasternack, and I'm from the University of California at Davis, and this is my presentation, Pacific Chinook Salmon Spawning Preference and Avoidance of Process-Based Flow Convergence Routing Landforms. Physical habitats are areas with characteristic attributes where organisms perform corresponding ecological functions. They're essential to characterize for river assessments, environmental flow regime development, and just river design for restoration or other projects. And you can see in these photos, there's lots of different kinds of little places where fish can do different things as well as other organisms. We have many approaches for characterizing physical habitat. They fall into two broad types: field data and statistical methods, such as a few of the ones listed here, and then assessment and prediction methods. And this is an important difference. So the first set here can only be used on real rivers, where you go out in the field and characterize them, and then you're only representing how they are in that real condition. The second one's different. You're characterizing a river based on a map and model analysis, but once you have that model in place, the physics don't change, so you can then run scenarios in which you change flow regimes or you change the topography, you add features to it. There's a lot of things you can do in a predictive mode. And we've seen lately that two-dimensional hydrodynamic modeling has come to the fore for both its predictive capability and its use in design for environmental flows and river restoration. So for example, here's an analysis where the colors show predicted habitat for Chinook salmon spawning on the lower Yuba River, California during the spawning season. And the area in blue is the highest predicted likelihood area where habitat should be utilized. And then white and red are areas that the prediction is that they won't be utilized. And you can see that the vast majority of actual occurrences of spawning took place following the pattern of that blue. So that two-dimensional pattern is something that we can really use. Unfortunately, even though we can characterize things very well, that habitat analysis doesn't tell us whether things are going to stay geomorphically self-sustainable when we build them. And we often see constructed landforms falling apart. For example, here's a place in the mountains where they built a riffle pool gravel-bedded channel in a mountain meadow. And you can see that flows scoured away all of that gravel. On the other hand, here's a place in the Central Valley of California where the riffles were made too narrow, all of the place material scoured out and deposited into pools. Scour in itself is not a problem. Rivers naturally scour and deposit. However, they do that in a way so that riffles grow and pools stay pools. If that doesn't happen, it's not working. And we see similar kind of things with meandering rivers where meander bends can be cut off or the outer banks are being cut away and the system is it's not self-sustainable, or it's just changing in a way that humans just can't accept. So we need to have a way to design things that can be self-sustainable. The research purpose here was to design and evaluate a set of fluvial landform archetypes where not only the terminology but the morphologies those represent are aligned with morphodynamic processes, so their fate is easier to understand and account for in design. In other words, we're not going to call things riffle, run, pull, glide anymore. We're going to call them something that's meaningful for morphodynamic processes. Specifically, the question asks whether a new type of landforms that we call flow convergence routing landforms, whether they not only can predict self-sustainability, which they're designed to do, but do they have any relevance for habitat? And in this case, I'm going to look at Chinook salmon spawning preference and avoidance. The hypothesis is that spawners will prefer the landforms called nozzle and wide bar, and they'll avoid ones called constricted pool and oversized. Furthermore, nozzle, while being preferred, is not predicted to be self-sustainable, while wide bar is. So I will explain these different landform types in a moment, but we have a very specific prediction and directionality for both channel change and habitat utilization. So what is flow convergence routing? It's a mechanism for morphodynamics in which the cross-sectional area controls where erosion and deposition occur. In general, erosion will always occur in the smallest cross-section and deposition will occur in the largest cross-section. Now at low flows, there's not a lot of action going on, but in general, we get very high velocities in the places that we traditionally call riffles. Riffles become narrow, and because their bed is high, they have a small cross-sectional area. So we get a convergence of flow that creates scouring conditions there. In the intervening pools, these pools tend to be wide and deep, and so they tend to be so big that they then can capture any deposition of material that's moving off the riffles or finer sediment going down the river. Now at high flow though, in a self-sustainable river, these things change. Specifically, to be self-sustainable, the riffle has to get substantially wider. And when it does that, the width can get so much bigger proportional to the fact that it remains a shallow, like it's a crest on the river, that with that extra width, the cross-sectional area is so large that now that becomes a depositional place. Conversely, pools, while they will remain deeper than riffles, can be so constricted that then velocity can accelerate to the point that they scour. So we have this two-stage mechanism where riffles go from being potentially places of scour to places during floods where they're definitely depositional, and vice versa for the pools. So we can take that concept and turn it into a landform test. We can look for places that are nozzles, which we define as both narrow and shallow, which I can kind of represent like that, and then oversized cross sections that are wide and deep. If we looked at it in a river context, you can see like a nozzle, here you see narrow and shallow, which is riffle, it's like converging here into this narrow spot, whereas the oversized upstream is super wide and deep. We have then another type we can use called normal, which is when we have an average depth and width compared to like along the whole river. It's the average cross-sectional dimensions. So those are 3 of the 5 landforms for this mechanism. The other 2 are wide bar, which is shallow and wide, and constricted pool, which is narrow and deep. And we can see this in a setting like this where there's no water, where here it's very, very wide, and then the flow will converge into this relatively narrow, stable pool. So we can test whether these 5 landforms actually exhibit hydrodynamics associated with self-sustainable morphodynamics, and we can test to see what habitat preferences there are. When we look at velocity as a function of discharge, going from base flow conditions past bankful to flood flows, what you can see for this river, the Lower Yuba River, is that at very low flows, nozzles are locations that have very high velocities and oversized very low velocities, which is what we would expect. As discharge increases towards the bankful, which is this number right here, a little after 100, they sort of, a lot of these converge, but nozzle gets particularly fast. But you can see that as we continue to go, compared to the normal condition here in the middle, we can see that constricted pool shown in blue actually accelerates how fast it's going and overtakes nozzle to become the fastest place on the river. So normally constricted pools should be deeper than nozzles, but because of complex cross sections, they can actually end up even faster. So we see a confirmation that these 2 landform types would expected to be erosional landforms, constricted pool and nozzle. On the other hand, wide bar and oversized are both depositional landforms. So wide bar, these are places that their width just increases so much with discharge, the velocity really slows down and they become depositional. So we can differentiate riffles into nozzles that are not self-sustainable and wide bars that are self-sustainable. So what we'd want to see then is, do fish exhibit a preference between these 2? And then if they do, well, that means it could be a harmful nuisance if we create nozzles, and it could be good if we were to create these wide bar settings. So to assess the utilization, we had 2 years of census-based RED surveys from rafts and kayaks, where every week we went out and mapped them with a sub-meter differential GPS. Across the 2 years, we had more than 6,200 REDs that were observed. We have a bioverification procedure based on an electivity index, which in this case is the simple forage ratio. What we do is we look at an area and we see, like in blue here, this area in blue is predicted to be high quality habitat. So we could look to see if the occurrence of organisms, the percent occurrence in that blue area is greater than the availability of that area. So we take the percent of reds to total, just considering that one area, and then we divide that by the percent area as like the bed area of that object, in this case blue, to total area. Now here I mentioned blue being high quality habitat. Well, for this study, instead of having these kind of complex patterns, we're just having straight cross-sectional rectangles where we're looking at flow convergence routing landforms. So do you have disproportionately more reds in, say, nozzle than the area of nozzle is present? And then when this number is greater than 1, it means a preference of that thing. And if it's less than 1, it's an avoidance. If it's about 1, then it's equivalent to just random occurrence for what you would get if you just had any sort of thing scattered around there. Okay, so I'll show you the results for the 2 years. On the x-axis is each landform as it was during the flow when the fish were spawning. And then the electivity index, when a value of 1 would be, again, no different from random. You could see that 3 of these are avoided and 2 of them are preferred. I also have on here bootstrapped confidence limits from doing random realizations and seeing time and time again what random data could produce. So if you're above the black line, we know above a 95% confidence that we have non-random preference by those organisms. Now, nozzles were highly preferred compared to wide bar, but they were both preferred, and wide bar would be self-sustainable. So if you're going to build something, that's what you'd want to build. On the other hand, oversized and constricted pool are highly avoided. In the second year, we saw less differentiation between the two, but they were both still preferred and these 2 were still avoided. So the important thing here is that, maybe there's more preference for these conditions, but again, these are unsustainable when floods come. So the conclusion is that flow convergence routing landforms are archetype geometries easily understood for how they will change over time. Flow convergence routing landforms show predictable, expected avoidance and preference by biota. Adult Chinook salmon prefer to spawn in riffles, yes, that's true, but riffles come in 2 varieties. One is self-sustainable and not. So rather than designing traditional riffle pool run glide, I would propose that we design for flow convergence routing landforms that are both biologically functional and geomorphically self-sustainable. Thank you.